development of innovative hybrid materials for electronic devices, biosensing, wearable flexible sensors, and enzyme mimicking applications. So without any further delay, let's welcome Dr. Surbhi, and you can start your presentation. Thank you.
Thank you, Partha, for such a nice introduction. As Partha already told you about that my area of expertise in hybrid materials and its multifunctional applications. So, I'll be giving a brief about one of a kind of metal gels or a hybrid material to you all uh, for its multifunctional applications. So, let's start with the talk. So my presentation is visible to all, as I think you can message me here. So
I think we are still on the first slide.
yeah, yeah, it's visible. So today's topic of discussion is metallogels as hybrid materials for applications as optical sensors, catalysts, and fabrication of electronic devices. So here is a quick outline of my presentation. Introduction of hybrid materials, metal organic gels, introduction properties and applications, non-covalent interactions, stimuli responsive and self-healing properties of these metallogels. And I have combined three of my works of these metallogels to get an insight about the practical applications of these metallogels and its futures perspective. So starting with the introduction. Hybrid materials are composites made up of combination of organic and inorganic components. For example, bone and oyster are among hybrid materials found in nature, whose inorganic part cause strength to the composite and its organic part leads to the bond between inorganic blocks and soft tissue. For example, core shell materials, self-assembling materials, nanocomposites, metal organic frameworks are some of its examples, which consist of organic as well as an inorganic counterpart. So among these hybrid materials, I have done some application work on metallogels. So I would like to give a brief about these metallogels. What are metallogels? As we know, gel are the material that resemble viscoelastic solids and are primarily composed of solvent and an elastic cross-linked network. When the molecular weight of gelator is greater than 3000, it is known as polymeric gel. When it is less than 3000, it is known as supramolecular gel. And this supramolecular gels involves non-covalent interactions as driving forces. So supramolecular gels can be divided into peptide-based gel, sugar-based gel, and metal organic gels. So metal organic gels consist of organic low molecular weight gelators and metal counterparts. Here, metal organic gels basically are those class of hybrid material which undergoes non-covalent interaction to form a self-assembly within the gelator molecules. Here, coordination interaction between ligand and metal ions is the main driving force between the formation of these metal organic gels. So as we can see that it undergoes non-covalent interaction to form a self-assembly and then undergo within the gelator molecules and finally forms a 3D entangular network which is known as supramolecular metal organic gel. So it coordination interaction basically ligand interaction between ligand and metal ions is the main driving force for this formation. So for the formation of these, we mainly focused on biomolecules as ligand because they are non-toxic in nature, they are cost-effective, eco-friendly, natural capping and reducing agent, and it can be easily accessible, stable, and their storage is easy. So these are some of the biomolecules. These biological small molecules can be used as low molecular weight chelators as ligand for the formation of this metallogel, such as amino acids, nucleobases, nucleosides, nucleotides, etc. So they are good for metallogel formation due to the presence of multiple hydrogen bonding as well as coordination site to which a metal ion can coordinate. So carbohydrate, proteins, and these lipids has been explored, but nucleotides class has been unexplored till now. So we have mainly focused on nucleotides for the formation of these macromolecules. Now, non-covalent interactions. What are non-covalent interactions? These are weak interaction between molecules or atoms that don't involve sharing of electrons. It is basically a type of electromagnetic interaction that occurs between molecules or within a molecule. So here are some examples of these non-covalent interactions such as electrostatic, van der Waals, pi interactions, and other hydrophobic as well as hydrophilic interactions. Now, these are some of the non-covalent interactions which are mainly involved in the formation of supramolecular macrogel, that is hydrogen bonding, ionic interactions, metal ligand interactions, pi-pi bonding, van der Waal interaction, host gas interaction, and hydrophobic interactions. So these are the main driving force behind the formation of this macrogel. These are some of the applications of these metlogels, like it can be used in sensing of gas molecules, heavy metal ion sensing, anion sensing. So as we can see, there is some fluorescence or something there in the gel. So there is turn on, and when these molecules interacted with this metlogel, it gets turned off. So we can sense some gas molecule, heavy metal ion sensing using these metlogel. We can also use them as electrocatalyst. They show semiconducting as well as conductive behavior, and we can dope it with some conducting materials. So they can behave like electrocatalyst, or they can also be used in electrolyte. This is a future perspective of these metlogel, which I'll explain you later. These can also be used for gas absorption. Dye absorption capacity is also there because they have porous structure, so they can absorb the dye and can be used for environmental remediation, biological activity. They can also be used for drug delivery application, and they can also sense use for biosensing application as well. These are some of the integrating properties of matrogels, like physical properties. It has swelling ability, porosity, thermal stability, mechanical strength, and its chemical composition and supramolecular structure is a good thing for some of the applications like electrocatalyst and environmental remediation application. Its biologically properties are biodegradation, antiviral, antibacterial, cytocompatibility is good. So Matrogel has two main properties which can be used for vast applications. So I'll be discussing these two main properties of these Matrogel. One is stimuli responsive property. So here, the as we can see that this Matrogel has as we can see that can this gel can react to chemical as well as physical stimuli. As we know that these metalogels forms from non-covalent and weak interactions. So when we apply some external stimuli on these gels like chemical stimuli, anion, cation, neutral chemicals, and chiral ghost molecules, they can disrupt these non-covalent interaction, and the gel network and the gel network can be turned into soul. And when we remove this stimuli, these can again reform without the stimuli. So this is basically some responsive stimuli responsive property, and these can also be physical stimuli like heat, UV irradiation, mechanical force, or some mechanic ultrasound force can be used. So we also used this metal gel for like photosensitive device. So as we can see, it can react with that photosensitive thing also. So it turns this light into electrical signals or um, current. Second is self-healing property. Self-healing is when we cut this metal gel in two pieces, then they again self-heal themselves. So this is an integrating property of these metal gel, which can be used in drug delivery systems, sensors, actuators, conductive materials, environmental remediation, catalysis, soft robotics, wound dressings, and protective coatings. This property also introduced with the property that it involves non-covalent interactions. So it has a fibrous morphology and 3D entangled network. So these when initially when these disruptions held, they deform their shape, and then when we rejoin these again attire in their initial state with these non-covalent interaction. So we have in my research work, we have mainly focused on its three main applications, as in catalysis, as an artificial enzyme, in optical sensing, and semiconducting electronic device. So I would like to tell you some brief about what is catalysis and what is artificial enzyme. So it is a synthetic, organic or inorganic molecule which mimic function of an enzyme. So these natural enzyme has some substrate. So if our material or matlogel uh, shows properties of these artificial enzyme, these can catalyze the substrate of these natural enzyme under physiological condition with similar catalytic mechanism and kinetics. These are some examples of artificial enzymes like oxidase, peroxidase, catalase, superoxide dismutase. And it also shows high catalytic activity, excellent biocompatibility, environmental favorability, ease for functionalization, low cytotoxicity, tunable properties, and stable as well as low cost. So we we can convert our material to an artificial enzyme for further biosensing application. So we further used these macrogels for optical sensing. So basically, optical sensor utilize light to detect the binding of a target molecule, and these can be utilized as a label molecule, which shows difference in optical signals such as changes in fluorescence and colorimetric changes. These sensors can be label free as well, which changes optical properties such as refractive index to sense the binding of the target molecules. So as we can see, analytes can be heavy metals, chemicals, pesticides, toxic gases, and these sensing elements can be our as synthesized materials, nanomaterials, metal nanoparticles, biomolecules, or as we can see matrogels, which shows changes in their properties, absorption properties, reflection properties, extraction properties. So if we get some change in these property, these are known as optical chemical sensors. And if we get changes in these current, voltage, and resistive properties, these are known as electrochemical sensor. As for now, we uh, we just tried to get these optical chemical sensor, and we are working on electrochemical sensors as well. Now, third application we focused for these macrogel is fabrication of semiconducting electronic device. So, we fabricated Schottky barrier diode using these matrogel. Our matrogel shows semiconducting behavior. So, basically, as we know, Schottky diode is a type of metal semiconductor junction diode. It forms junction of semiconductor with a metal. So, as our material was semiconducting, we used our material in place of this n-type silicon and metal for the fabrication of these Schottky barrier diodes. So it offers fast switching action, has a low forward voltage drop, and these p-type n-type join together to form p-n junction. And we used silver or aluminum electrodes as metal instead of p-type semiconductors. These are some examples of Schottky barrier diode. It can be used for controlling reverse current in power supplies. Schottky diode can be used in radio frequency appliances, circuits of logic gates, and can be used for designing rectifiers as well. So these are the main application we focus using these materials. So I would like to show some work we have done in our laboratory. So this is something copper inosine supramolecular metal gel. We use copper as a metal and inosine biomolecules, the nucleotide, as the ligand for the formation of supramolecular metal gels for further optical biosensing applications. So we mainly focused lacase enzyme-like activity and peroxidase-like activity. So I would like to give a brief about these two enzymes. So lacase is a copper-containing oxidase enzyme present in many microorganisms, plants, and fungi, widely used for oxidation of several biologically relevant phenolic as well as diamine functionalized substrates. So here, it is the schematic representation of lacase mimetic activity of some. I have taken some microstructure example that this microstructure shown some lacase like activity. So 2,4-DP and 4-AP here. This is 2,4-dichlorophenol is the main actual reactant, and this composite copper oxidizing oxide composite catalyzes this oxidation to form a radical product that is red in color and which then reacts with 4-AP to form red color product. So these are two substrate of this enzyme, and when we interacted our catalyst or something this composite material with these, it shows red color adduct, which tells us about that this material shows this enzyme mimicking activity. Further, we also characterize with the UV visible spectroscopy, and after that, we also did kinetic study of these enzymes. So further, this property can also was used for the epinephrine detection. Epinephrine is a neurotransmitter which causes harm when its level is increased in human body. So this properties converts epinephrine to adenochrome, which is brown in color. Second enzyme we focused is peroxidase enzyme. So basically, it catalyzes the oxidation of H2O to hydrogen peroxide into hydroxyl radicals, which further participated in electron exchange with substrate, producing color on oxidation. So here, this is TMB. TMB is the substrate for this peroxidase, and it converted when interacted with the catalyst or composite we synthesized. It oxidized this substrate and gives us blue colored oxidized TMB. Further, we sensed glutathione using this as a glutathione is reducing in nature. So this again reduce this oxidized TMB and get it colorless. So we sensed glutathione using these peroxidase like activities. So in this work, I have told you copper inosine metlogel. This is the basic schematic for the formation of this metlogel. The biomolecule is inosine, and we added NaOH and copper at different molecular ratios, molecular weight, and at room temperature. After 4 or 5 hours, we just get this self-starting metlogel, which has entangled fibrillar network. Here is the electrical conductivity of this matlogel, which shows that it can also be used in electronic devices as a conductive material. So here is some circuit was connected when these are apart. There is no blinking of this LED, and when they come close, there is blink of this LED. So we calculated its conductivity. Further, it has been used for lacase-like activity and oxidation of some phenolic substrate, and it also sensed epinephrine and dopamine with these limit of detection, which are good, which are comparable with the literature. So, as I have told you earlier, that it is a copper-containing enzyme. Widely used for oxidation of several biologically relevant phenolic as well as diamine functionalized substrates. Here is the digital image of this system. When these substrate are there, these are colorless. When we added our copper inosine metal gel to it, it changes its color, which shows that this copper inosine metal gel shows enzyme like activity. Then peroxidase like activity was also done by this metal gel. So here we sense glutathione with 0.047 micromolar uh, limit of detection, which is good. And these are the rate of these reactions, which we calculated from this UV visible studies and its kinetic studies. Here is the digital image of oxidizing of this substrate of peroxidase, which gets oxidized and gives blue color. These gels also show self-healing behavior, which I've told you earlier that its property is there, metal gels property is there. So when we cut them down, they are apart, and when we just bring them closer, they again recombine and rejoin them, self-heal themselves. So here is the self-healing ability of these metal gels. And further, it is stimuli responsive for different this acid and bases. So when we added some different acid and base to it, it converts this gel to sol. And when we again remove this stimuli, they again reformed and give this. So this thing can be used for drug delivery applications as well. So this is a good property of these materials. Here is some another work in which we synthesize stimuli and self-healing supramolecular zinc guanosine metal organic gel for Schottky barrier diode application. Here, this is the basic schematic of these guanosine and zinc-based metal gel. Here is the fibrous morphology of these metrogel, which shows that this is a 3D entangular network, and it also shows the porosity of these metrogel. So, to know about get an insight about the mechanical robustness and thixotropic properties of these metlogel, we conducted this rheological analysis test, which shows that these gels has mechanically robustness and thixotropic. Because as we can see that its loss modulus is less and storage modulus is high, so it shows that this gel is mechanically compatible. Further, we also tested this metalogel for Schottky barrier diode fabrication. So we fabricated it on ITO-coated glass substrate. Then we put it our metalogel on this, and then get fabricated this EAG electrodes on that and created a Schottky barrier diode. So here we see a non-linear rectifying nature of this Matlow gel based Schottky barrier diode, which is a Schottky diode characteristic, and further calculated its band gap and other things, other charge transport characteristic, which shows that it shows the property of Schottky barrier diode. I have included very less results in this, but to get an insight about this, I just put it some of its results. In another work, we again synthesize multi-stimuli and self-healing zinc inosine supramolecular metal organic gel for phase selective gelation and application as a light responsive Schottky barrier diode. So basically, here we fabricated synthesized inosine is a nucleotide, inosine and zinc-based metal gel at room temperature, and it shows a standing metal gel with a fibrous morphology. And this gel is transparent in nature, shows us 93.55% transparency, which can be used in soft electronic devices. So this is a good thing. We are also trying to fabricate this metal gel on this glass substrate, and this is almost transparent, so we can use to as an alternative ITO if it's good us give us good conductivity. So this can be used for a transparent conducting film as well. Now, these are used for phase selective gelation. So phase selective gelation is basically the ability of gelator, this gelator, when we convert this gel into zero dry gel. So this dry gel, zero gel, selectively gel one of the solvents in a mixture of two or more solvents. This is commonly known as phase selective gelation. So as as we can see, it was found that when we add zinc ionosine zero gel to an water mixture, oil, there is a oil water mixture, petrol and water, pump oil and water, olive oil and water, mustard oil and water, silicone oil and water, coconut oil and water. So when we added the zero gel of this matlo gel, so they it in this oil water mixture, it resulted in gel formation with a water layer, while oil layer was undisturbed, which can be separated from water by simple decantation. So it shows that it selectively gel with water, and some other mixture like oil and all can be decanted using this zero gel. Further, zinc ionosine zero gel was also utilized to remove polar impurities such as dyes by entrapment of dye in gel mixture. So when this zinc ionosine zero gel was added to a mixture of containing dye and water, as we can see here, dye and water. So uh, when zero gel was added to a mixture, it contains water, lime water, and hexene. So it selectively gels up with water containing dye, and as we can see, it reformed with the dyed water and decanted the hexene. So finally, we got this zero gel, dyed zero gel with this. So it selectively gels up with water, and we can decant some oil water mixture from as we can see that there is some traces amount of water in petrol. So we could decant water from that petrol when we add this zero gel in petrol. Further, we also utilize this metal for photosensitive Schottky barrier diode fabrication. This is an example of its similar responsiveness with photosensitivity of Schottky barrier diode. So it converts the photo energy into current flow basically. So we can see that IV characteristic shows non-linear rectifying behavior. Uh, Amplifying of Schottky diode nature. And further, we also calculated charge transport characteristic for this device and got better results as we did from our previous literature work. So these are some of the works we done till now. This is something different work. I would like to I would like to brief about it. This is not relevant to Metlogel, but we could incorporate Metlogel in this work. So basically, in this work, we fabricated a graphene and polyaniline graphene sensor. So there is a sensor structure, sandwich structure, in which we used PDMS layer and then grown graphene on it and CVD using CVD and deposited again a PDMS layer or then polyaniline layer basically, and then again no, combined polyaniline layer deposited graphene third layer on graphene plus polyaniline layer and get a GPT sensor, graphene, polyaniline, and graphene sensor, which we further utilized because this sensor shows change in resistance with motion, touch, and wrist pulse breath sensing using this sensor application. So we are trying to incorporate a Matlogel in case of this graphene. Graphene is conducting and this polyaniline also conducting polymer. So when we increase the conductivity of our metal gel using some doping and all, so we could also fabricate this kind of sensor using metal gel as well. So this work has been published in IEEE, and we also get patent of this DPG sensor. So we could incorporate something new in this fabrication structure as well. So some future perspective, we are working on these things. Metal gel can be used as solar cell, flexible sensor, and a semiconducting electronic device. We can use lanthanide metal, lanthanides for this. Till now, we have used transition metal ions, so we could use lanthanides. That gives us some different properties or luminescent properties of these gels, and we could utilize them for further applications. So, solar cell, as we know, it transforms light energy directly into electrical energy using photovoltaic cells. So a thin P-type semiconductor layer atop a thicker N-type layer, which with electrode that allow light penetration and energy capture. So light photon create electron hole pair at the P-N junction, generating a voltage capable of driving a current across the across the connection load basically. So its material characteristic, the material we have to choose for this solar cell application, the band gap should be close to 1.5 electron volt. It should had has a high optical absorption and electrical conductivity, with silicon being mostly used, commonly used for this purpose. So its uses is in a calculator, wristwatch, and in spacecraft, highlighting its versatility and growing importance in renewable energy systems. Now, what are particularly dye-sensitized solar cells? These are low-cost solar cell belonging to the group of thin twin solar cell. So, based on semiconductor formed between a photosensitized anode and an electrode, a photochemical system. So, its construction is like that. It consists of ITO, FTO gas substrate, and then transparent semiconductor conducting metal oxide nanoparticles, dye sensitizer, electrolyte, and counter electrodes. So here is a typical DSSC fabricated in a lab. So its advantages are many. It had low fabrication cost and simple configuration. So its limitations are that leakage or volatilization of liquid electrolyte is there, and owing to no solvent, solid state electrolyte also shows low ionic conductivity, leading to poor photoelectric performance of corresponding this dye sensitized solar cell. So there is a need of quasi solid state electrolyte that could promise alternatives which offer excellent potentialities to fill the gap between high power conversion efficiency and long term stability. So now we'll be proposing, like we are working on this, that we could use our metal gel in place of this electrolyte, which can be used as quasi-solid state electrolyte in this dye-sensitized solar cell. So here is a basic scheme that to form this solar cell. So so metal gel can be used for high mobility, ultra thin thickness will be there, large specific area will be there, excellent thermal conductivity, biocompatibility, and quick stimuli response will be there. When light interact with this metal gel, we can quickly stimuli response and quickly convert this light energy to current. So our basic approach is to form metal-based coordination-driven metal gel electrolyte by absorbing liquid electrolyte with metal organic gels and apply it to quasi-solid state dye-sensitized solar cell. Further, its characterization will be done. Electrical impedance spectroscope measurement and photovoltaic characterization will be done. So here is the basic idea that we could use, because this is somewhat unexplored and less explored thing till now. So we could use it as an electrolyte for future applications. And as I told you earlier, that it can also be used as flexible sensor. In earlier work, we use graphene and this polyaniline. So flexible sensor, basically, it is a device which measure how much a surface bend or deflects. It's often attached to a surface and the sensor resistance change when the surface is bent. So amount of deflection is directly proportional to the resistance. To date, carbon CNT, graphene, carbon black, and graphite, liquid metal, conducting polymers, and metal nanomaterials have been widely employed in preparing multifunctional flexible sensors. So we could use magnogels in place of these sensor material because of its high mobility, specific area, thermal conductivity, biocompatibility, and as well as quick stimuli responsiveness. And PDMS will be used as flexible substrate on which a matrogel will be fabricated because of its good transparency, chemical inertness, stability, and its surface property can easily be uh, changed or controlled by UV irradiation or through different electronic components which are strongly bonded to the substrate surface. So further, these metalogel can also be used as strain sensor, temperature sensor, as well as pressure sensor. So the work we have done, we fabricated that graphene and all can be replaced using metalogel. So the conductivity of these metalogel can be enhanced using some doping, or we could directly synthesize conductive metalogel, which can directly be incorporated to these kind of flexible sensors. And finally, here is the basic scheme that I've shown you earlier. So we could use this metal organic gel as a sensor. And lastly, we could fabricate lanthanide based metal organic gel based Schottky barrier diode. Till now, transition metal ions have been explored for this fabrication of this diode. So we discussed earlier, that it's semiconductor diode formed by junction of metal semiconductor, and it has low voltage, forward voltage drop, and fast switching action. So we could construct it using ITO coated glass substrate as a substrate basically for the fabrication, and then a thin layer of matte gel, lanthanide matte gel on ITO coated glass substrate will be applied using spin coating, followed by vacuum oven drying for a few minutes. And then AG electrode were deposited as round spots on the surface of the semiconducting device, utilizing a shadow mask. And finally, device characterization will be done using ITO, Mertelogel, and some metal electrode sandwich structure. And finally, IV characteristic for the device will be studied by recording the IV plot. So this Schottky barrier diode can also be used using lanthanide based metal organic gel. So these are some future perspectives of these metal organic gels. So here some of my list of publications of these metal gels and all. So you can go through them if you want, and I could share with this with Partha these all publications details. So these are some of my work relevant to metal gels and hybrid composites. So this is all. If you thank you for listening for this presentation. If you have any questions, I could deal with them and just tell you about that.
Thank you, Dr. Surbhi, for your nice and insightful talk on metalogels. Now the floor is open to Q&A. Yeah, I think we have one question in the chat box. You
Okay.
can, yeah,
Um, Actually, graphene layer was firstly deposited on like copper substrate. Okay, and then that copper substrate was further deposited on this our PDMS substrate. As I'll show you that in my presentation. Yeah. So firstly, graphene was grown on copper foil, and then it is deposited on PDMS, because copper foil in was like diluted in some solution of this ferric nitrate, which dissolves the copper foil into it, and then we transferred it into PVA, and then that PVA layer also dissolved in acetone, and then we fabricated it on PDMS layer. Then polyaniline layer was deposited on this graphene. Polyaniline layer was simply some skin coated on this, and third layer of graphene was again deposited using this method only. So this is the whole thing we did for the process. Thank you. Any other question? Partha, your voice is not audible. Unmute yourself.
Yeah. Any more questions from the audience? If not, I have two questions.
Yeah,
So you talked about the fiber entanglement in your SCAB image, right? That
yeah.
your Metlogels is a 3D interconnected network. So is there any way we can, rather than making a hydrogel, can we make different platforms like films or other substrates, something like that? Like
Using
we
this
can align
methodology.
those fibers. Yeah,
Yeah, you want to align some
yeah,
these fibers in some different techniques.
yeah.
Yeah, we could actually we are trying to fabricate. We have just fabricated on this simple thin film, ITU thin film. So these are not flexible enough. So we are trying to fabricate these on flexible sensors so that we could manage to flexible them and change their coordination bonds and all. So we need some doping of some conductive materials into these matrologers for use on some different substrates. So we are trying to cope with this. As you know that we added polyaniline in graphene to make fill these gaps of these graphene structure to polyaniline, and then sandwich again graphene so that their structure cannot be deformed. So we could use some other material as well with this matlogel to get its conformation stable and can be used for wearable flexible technology.
Okay, thank you. One more question on porosity. You told that your metal gel is has high porosity, right? Have you measured the porosity
No,
anywhere?
no, we haven't calculated because
Okay,
we are trying to use it for supercapacitor application, but we have to combine it with some carbon material as well to get some much more it is known for its porosity, but we haven't used it for some particular application. So it hasn't been done using this PET surface analysis and all.
okay.
We are trying for it.
And one more last question is on transparency. You showed one graph on transparency. So how you measure generally?
UV spectra basically.
Okay,
We just put it in this UV visible spectroscopy and calculated transmittance. Direct transmittance mode will be there. Absorbance transmittance mode is there. So we calculated directly get the graph of this transmittance using UV visible spectroscopy.
okay. Yeah. Last one question I have. In one of your slide, you talked about enzyme mimicking activity, right?
Yeah.
So you told that the color basically change when you add those chemicals or the additives. So is there any like mechanism that leads to the color change? Or like
Yeah.
why only those specific chemicals? There might be,
Actually,
as far I know, like there is a color changing pigment like anthocyanin, right? That also kind of mimics those enzymes. So why only that specific
yeah,
pigment?
basically, as I've told you earlier, that in lead case, we used some. uh, chromogenic dye. Basically, it gives color when reactive oxygen species react with like our material should be having some catalytic sites. So some reacting oxygen species react with that substrate and leading to oxidation of that particular substrate. So some involvement of reactive oxygen species in the catalytic sites of our synthesized material will be there, which reacts with that substrate and gives then when oxidation helps, it further shows change in that chromogenic dye. We use chromogenic dye for color showing, like it shows color. And further, we use a kinetic study model, Michaelis-Menten model, to fit the this kinetic study, and calculated this Michaelis-Menten constant and all for these dyes and all. So, so basically, there will be presence of reacting oxygen species will be there. So due to this, this happens.
Okay, thank you. Yeah, I think if
Thank
there is
you.
no more question, thanks again for your nice talk, and
Thank you.
hope to see you for next seminars at for MSE-GSE. Yeah, thank you
Thank you
for.
so much, Partner.
Yeah. So you're
Thank
ending
you.
the session here. Yeah, thank you.
Thank you.